Fijnstof lijkt een probleem van vandaag, maar lang voor er auto's, fabrieken en houtkachels waren, kon het ook al in de lucht belanden, met desastreuze gevolgen. Planeetonderzoeker Cem Berk Senel van de Koninklijke Sterrenwacht en de VUB toonde aan dat de meteorietinslag die het einde van het dino-tijdperk inluidde, zoveel fijnstof de lucht induwde dat het jarenlang donker bleef op onze planeet. Hij is een van de 5 laureaten van de EOS-pipet 2024. Welkom bij Vraag het aan, de podcast van EOS Wetenschap. Hi Cem.
Hi.
Congratulations for your nomination for the EOS pipet. The jury was impressed by your research on the end of the dinosaurs. What exactly did you discover?
We discovered a coherent mechanism that steered the last terrestrial mass extinction 66 million years ago. In other words, that's the end of dinosaurs and most of the other species on Earth at the Cretaceous-Paleogene boundary.
Can you take us back to 66 million years ago and describe what happened on our planet?
Almost 66 million years ago, the world was dominated by lush vegetation, thriving ecosystems, and towering marvelous creatures like T-Rex and more. But this harmony was disrupted by a colossal asteroid bigger than Mount Everest. The Chicxulub asteroid impacted our planet in what is now Yucatan Peninsula in Mexico, with an impact energy equivalent to more than billions of Hiroshima atomic bombs. And this huge energy triggered a massive amount of impact ejecta in the atmosphere, involving dust, sulfur, soot, and other climate-active agents in the atmosphere, which stayed in the atmosphere more than 15 years. And this triggered a nuclear winter with extreme cold and global darkness and food-deprived conditions that led to the demise of dinosaurs and most of the other species at this Cretaceous-Paleogene boundary.
So it was dark on our planet for many months or years or decennia?
From our computer simulations, the global darkness and the shutdown of photosynthesis take up to 620 days, which is almost 2 years after impact.
Yeah. You're talking about days and almost 2 years, and this research is about something that happened 66 million years ago. So 2 years is very accurate. How is it possible to be so accurate?
Yeah, this is thanks to the power of computational models and advancement in computer science, because thanks to the computational models, we could reproduce the past, present, or future ecological events with the timescales of seconds up to centuries or millennia or even longer.
So you use computer simulations and computer power, but what source do you use to research and to go back so long in time?
So yeah, of course this is thanks to the computational models, but assisted by the geological records, inputs and reconstructions. For example, paleogeography, plant functional types at Cretaceous, at late Cretaceous, the emissivity, albedo, and this kind of information, and also in impact focus, the amount and the optical characteristics of the ejecta constitutes, for example, dust, sulfur-bearing gas, black carbon, and soot. So these are all driven by the information coming from the geology. Yeah. So it's the combination of the computer models with the geology.
Yeah. At school, we were already learning about this asteroid impact that marked the end of the dinosaurs. What does your research add to that, what we already knew?
So first of all, our research builds on the existing hypothesis of Alvarez in 1980s, who came out with the impact-generated dust-driven mass extinction. But this hypothesis was later ruled out by the following works in favor of other atmospheric agents as the main culprit of the KPG mass extinction. This involves sulfur-bearing gas from the impact site or soot or black carbon emissions from the global wildfires. However, here in our study for the first time, we provide physical evidence from the field works in North America, as collected by Dr. Pim Kaskes from VUB, AMGC and the team, and analyzed in the laboratory and integrated into our computer models, which are palaeoclimate models at the observatory. So for the first time, we provide an information based on the combination of physical evidence and high-resolution computational simulations.
Mm-hmm. You talk about a hypothesis. Can this new research make it to fact that it really happened like this?
Yeah, because this is based on the real physical data from the fieldwork, the samples collected, and then the dust information is revealed from laser diffraction analysis from the laboratories. And then this physical and real data put into the computational models and to assess the relative and combined effects of all impact ejecta constitutes. And then we end up with these climatic perturbations, which shows that the dust was the main culprit or steered the mass extinction mechanism.
Yeah. So the dust was the absolute killer in this story?
Yes, exactly. So we could say this way: dust was the main culprit and the prime climate active agent in the atmosphere that halted photosynthesis and collapsed the primary productivity.
So this asteroid impact was huge for life on our planet, but not all life went extinct. How come that not all animals and plants died?
Some species exhibited superior adaptations to the post-impact environments by entering a dormant phase through seeds or hibernations or hiding in burrows or shelters. And another thing is the species with more versatile or flexible diets, not dependent on one particular food source, managed to survive while others went extinct. Also, small mammals are one of the successful examples that survive in the in the aftermath and try to date.
Yeah. You already told something about how you came to your insights. Can you elaborate a bit more on that? What research, what experiments did you do?
So, our insights were derived from the combination of fieldwork, as I said before, and laboratory analysis and computational modeling, which allow us to piece together the puzzle of the last terrestrial mass extinction. Yeah. So it's an interdisciplinary work.
You built a so-called palaeoclimate model to simulate the climatic and biological response of the impact. How did you realize this model? How did you make it?
So this model, first of all, was based on the planetary atmosphere model that we have designed and developed at the observatory for many years for other scientific projects. For example, understanding the global dust storms on Mars, modeling the haze on Titan and Venus and Jupiter. So it's a general purpose planetary atmosphere model, which we call Planet Dwarf. Here in this case, we specialize this model for Chicxulub impact scenario at the end of Cretaceous. But we need, like we discussed before, geological constraints for this model. For this purpose, we constrain our paleo-Earth specialization of Planet Dwarf model into Chicxulub impact, thanks to the information coming from geology. So it's the integration of our paleoclimate model with available geological constraints coming from 66 million years ago.
Yeah. Could an impact like the asteroid that killed the dinosaurs, could that happen again?
So yeah, it's less likely, but maybe in next 50 million years or 60 million years, but maybe not for our species, but for other extraterrestrial forms because of this global climate crisis. If that brings the end of human species, maybe another Chicxulub impactor size projectile that could lead to the demise of other forms, but not now. But yeah, I mean, in millions of years.
Yeah.
Statistically, because such impactors could enter the orbit of Earth and make the collision course with Earth with 50 millions or 100 million years of time scale.
Lots of children, they love asteroids, they love dinosaurs. In your research, they are both present. Have you fulfilled an ultimate childhood dream?
Yeah, absolutely, without a doubt. As a planetary scientist, it was an extraordinary voyage for me, working on my passions, my truly passions for meteorites, planets, and the marvelous world of dinosaurs. So it's really the blending of these passions with my scientific curiosity, of course, while contributing to understanding of the Earth's captivating history, I would say.
Yeah. The focus of your PhD was not only on dinosaurs or asteroids, but on planets. What exactly did you research, and what research do you do now?
In my PhD, I work on the multi-scale modeling of planetary boundary layers on Earth and Mars. Planetary boundary layers are the lowermost and turbulently most active part of the atmospheres, which is lying from few meters during the nighttime till 1 to 2 kilometers on Earth. But on Mars, things are getting more crazy. The boundary layers can reach even up to 12 or 13 or 14 kilometers. So I specifically work on understanding and modeling of boundary layers because that's the place where we live in. Because it's directly influencing our daily lives. Because that's the place where the Earth's surface blend with the atmosphere. So in my PhD, I developed multi-scale models from global to mesoscale and microscale levels of boundary layer phenomena, specifically the turbulence modeling, which is a chaotic state like another chaos that we see in Chicxulub impact case. So I developed a couple of turbulence models to use in modeling planetary boundary layers on Earth and present Mars.
Mm-hmm. What do you hope to learn by studying these layers?
So these layers are the lowermost part of the atmosphere, which is prone to dust storms, hurricanes, and precipitation, and other environmental extremes. So by working on boundary layers on Earth and Mars, I developed these models to understand the exchange processes between the surface and the surrounding atmosphere, which could help understand different environmental events in the past and present of Earth and Mars. That's how I can apply these models for this dino story. That's why and how I can apply this model to understand the globally encircling dust storms on Mars.
Yeah. In the research with the asteroid and the dinosaurs, it was about the extinction of a lot of life because of an impact. Could you use this knowledge also to know if there was life on Mars in the past?
So not exactly the similar way, but in my postdoc funded by FVO. My final work package will be addressing the mega early Martian impacts to understand the disappearance of water bodies. Again, it comes to the modeling of the planetary boundary layers on Mars, and link with the lower and upper atmosphere. So it's quite relevant to also other events in the past, present, and future of planetary atmosphere. So there are direct links of this Chicxulub impact research also to understanding other impact processes or events in the history of Mars.
What other research are you doing now, or do you want to start?
So for the moment, I'm working on a DART impact model. DART is the double asteroid redirection test. That was a successful space mission held by NASA in September 2022. The objective of the mission was to deviate the orbit of the binary of a double asteroid system, which is called Dimorphos, around Didymos. So it's a double asteroid system. As a result of this space test, the DART spacecraft impacted into Dimorphos and successfully altered its orbit almost 32 minutes. So for the moment, as being involved in HERA impact modeling team, I work on the possible or potential conclusions of DART impact, understanding the cratering and ejecta processes.
What do you find the most fascinating on being a scientist in this matter?
All these incredible stories, but more generally, it's seeking my curiosities in science, asking big questions and following them, and reading a lot, and even thinking about those questions while sleeping. So to me, it's this big curiosity and asking continuous big questions.
Thank you very much for this very interesting conversation, and good luck with the rest of your research.
Thank you very much for this podcast.
En jij, beste luisteraar, bedankt voor het luisteren naar deze speciale aflevering van de EOS-podcast Vraag het aan. In deze en nog 4 andere afleveringen van onze podcast praten we telkens met één van de laureaten van onze EOS Pipet 2024. De EOS Pipet is een prijs die EOS Wetenschap uitreikt samen met de Jonge Academie aan de meest beloftevolle jonge wetenschapper actief in Vlaanderen. Wil je ook de andere laureaten leren kennen, wat zeker de moeite is, wat ik zeker kan aanraden? Surf dan naar eoswetenschap.eu/eospipet 2024 of luister natuurlijk naar de andere afleveringen van deze podcast. Tot een volgende aflevering. Dag!